Yes, hello everyone, and thank you for your interest in the surface loading analysis tool. Basically, what we are going to do today is to introduce the CEPA surface loading calculator. So it's going to be a fairly quick presentation, maybe 30-35 minutes. And so let's start without any further ado. Here is the agenda of what we have for today. So I'm going to talk about the background and objective of the analysis, a surface loading stress analysis, right? So we understand what the tool is, how the tool is going to help us. Then I'm going to give you a brief introduction of different stress components that a surface loading analysis should account for, should basically include in the calculations. Then we have, CEPA is not the only tool. There are other available tools on Technical Toolboxes, in case you have access to Technical Toolboxes Hub. So I'm gonna explain some of those tools, again, very briefly, because this is a short seminar. We don't really have time to dive deep into the guts of each model, but I'm going to explain and then contrast, advantages of CEPA versus the other models. And then, we have an introduction to the CEPA tool, so you can see in real time some of the elements. And finally, we have a Q&A. Hopefully, we are going to have like 10 minutes or so, or 15 minutes for Q&A near the end. All right, so let's start with surface loading. And usually, I like to change my pointer to a laser pointer. Okay, there we go. All right. Okay, this is, I'm not with Technical Toolboxes. The company that I work for and I'm a partner in is RSI Pipeline Solutions. So it's a company that we started, almost 4 years ago with 2 other colleagues, plus John Kiefner. So there are 4 of us who started the company. And this is a quick introduction on the company, the different services that we offer. Basically, we are mainly a consulting company in the area of pipeline integrity management. Okay, so let me pass this. And so the background of this CEPA model is the CEPA model basically is using the Spangler-Iowa equation. There is an equation, famous equation, that is known as Spangler-Iowa equation that was originally developed by Spangler in Iowa State University, and it was mainly used for design of culverts, right? Originally, it was unpressurized culvert. And there are different versions of the model. There is a version of the model for concrete culverts that are more rigid, and then for corrugated metal culverts that are more flexible. So later on, that model, or that equation, I should say, was modified a couple of times by different people. The latest version that is known as the CEPA model was developed by Kiefner and Associates, by Dave Warman. Back then, he was with Kiefner and Associates. So just a little background on the CEPA model. And CEPA stands for Canadian Energy Pipeline Association. So the reason we call it CEPA model, because this project that was completed by Kiefner and Associates, it was funded by CEPA, right? That's why it's known as the CEPA model. And again, if you're interested to learn more about the theoretical background and also the historical background of the model, here I have listed a bunch of papers, which I think they are mostly, or at least some of them, If you do a Google search, you can find the report on the CEPA website. And the last one is an IPC paper. So again, if you don't have access to IPC papers already, you can purchase this article probably for $20, $25. All right, so the objective of a surface loading analysis, this is also known as encroachment. And encroachment could have many different meanings. For example, in the context of pipeline engineering, any type of activity within the right of the way or near the right of the way that can cause stress or pressure or vibration on a pipeline, it's called encroachment in general, right? Like, for example, a blast operation, because it can cause vibration and affect the pipeline, or pile driving operation, and so forth. So the CEPA model, the focus of today's seminar is just surface loading from vehicles. If a vehicle crosses a pipeline, that's called surface loading, stress analysis. That's the type of analysis we perform to make sure that the pipeline is safe, right? And the things that we account for, or basically the objective of the analysis, is to calculate the stresses in the pipe, longitudinal stress, circumferential stress, whatever, and to show that those stresses are acceptable, right? Now, the acceptable limit that we use in a typical surface loading analysis is 90% SMICE. By the way, 90% is not the default value in the calculator, but 90% is the value that the commonly used standards in North America recommend. For example, ASME 31.4 and ASME 31.8. They have a 90% limit for the equivalent stress. Equivalent stress is the combination of the circumferential and the longitudinal stress, right? They have a 90% limit. And then there is also a 90% limit for the additive circumferential stress. And I'm going to explain a little bit more what is the additive stress versus hoop stress from internal pressure. So that 90% also same applies to Canadian standard. I believe the limit that they have for the combined stress in Canadian standard is 90% SMICE. The point is that 90% SMICE assumes that the pipe is in good condition, right? That the pipe material and the weld material, they are in compliance with whatever code and standard they are supposed to be. That there is no additional stress. The assumption here is that the stresses, because the surface loading calculator accounts for the pipe internal pressure, for differential temperature, and for surface loading, soil overburden, and the vehicular load on the pipe. If there are additional loads, stresses on the pipe from other sources, they have to be accounted separately, right? So that's another assumption. And if the pipe has features such as ILI features, such as metal loss or dent or cracking, etc., crack-like features, again, they need to be treated separately, because the surface loading tool assumes that the pipe is free of such features, right? And another understanding is that whoever is running the analysis have a good understanding of encroachment problems, both in terms of theoretical understanding of what is going on and how we do the analysis, the calculations, and also understanding about that particular location for which the analysis is being performed. Because there could be certain conditions that the tool doesn't know, so it doesn't, include in the calculations. I'm just going to give you some quick examples. If you have I gave you one example already in case you have features such as dent and metal loss, etc. Right, so that requires a separate treatment. But if you have features such as fittings, T connections, valves, or even segments and sidements, if they are more than about a few degrees, those are the things that may require a higher level analysis. So basically, the goal of the analysis of a CEPA analysis is to check the stresses in the pipe and make sure that the structural integrity of the pipeline will not be compromised due to the extra load from the vehicles that cross the pipeline. And common checks is the additive circumferential stress, which is the total stress from operating and from surface loading, right? So we have some stresses from the internal pressure that has to be accounted for. We have some stresses from the vehicle that has to be accounted for, and then some stress from the soil overburden, right? So when you calculate them and add them up together, that's called the additive circumferential stress. And then similarly, we have an additive longitudinal stress with different components from internal pressure, from surface loading, and from differential temperature, thermal load. And then the combination of circumferential and longitudinal, because when you have biaxial stress, the combined effect of biaxial could be worse or better than each one of the stresses individually. All right, so let's quickly look at different components from stress. For the circumferential stress, we have the existing stresses in a pipe from operation, right? There is the internal pressure in the pipe, which usually we use Barlow's equation. Here on the right-hand side, I have a sketch that basically shows the Barlow stress in a pipe. Right, so we have internal pressure, stresses from internal pressure, and then we also have stresses from, we have longitudinal stresses from differential temperature or from the pipe pressure, right? So when you pressurize the pipe, because the pipe is restrained longitudinally, again, this diagram schematically shows the situation, this green pipe over here. When you pressurize a pipe that's buried, the pipe wants to expand because of the internal pressure, because of the ratio. It circumference as a result of the Poisson ratio action. It wants to shrink longitudinally, right? But the soil friction prevents that. So as a result of that, you get a tension in the axial direction of the pipe. So that has to be accounted for. And then we naturally have the differential temperature. If you bury the pipeline at a certain temperature, if the temperature increases or decreases after the pipe is buried, that can create thermal stress in the pipe, right? So that has to be accounted for as well in a surface loading stress analysis. All right, so what else we have? We also have existing stresses from soil overburden. And what I mean by that, again, this sketch over here shows that schematically. You have a pipe, there is an overburden, a backfill over the pipe, right? Soil backfill. That overburden applies a pressure to the pipe. So that has to be accounted for. And naturally, the surface loading. When you have a vehicle that crosses this pipeline, that can create additional stress. That's known as the traffic load or live load on the pipe. All right, so here again are the equations. Again, because this is a quick seminar, I'm not going to go through the details of the equation. I just provided them here just to give you like a quick introduction on how the calculations are performed. So for example, for hoop stress or circumferential stress, we have to account for the Barlow's stress from pipe internal pressure, right? Then there is a stress component from soil overburden, which we have to account for. And then there is also a hoop stress from surface loading from the vehicle. So I call it live stress. That has to be accounted for as well. And similarly for the longitudinal stress, we have the Barlow component from the Barlow's equation from pipe internal pressure. Here we have the thermal stress, right? This is alpha E delta T. Alpha is the coefficient of thermal expansion. E is the Young's modulus. Delta T is the temperature differential. Then we have another component from soil overburden, and new here is Poisson's ratio. Then we have a local bending and global bending. This last component over here, these two. These are traffic stresses, live stresses from the vehicle. When a vehicle crosses a pipeline, there is a global bending moment in the longitudinal direction, and there is also a local bending. So again, in the hoop direction over here on the left-hand side, what happens is when a vehicle crosses the pipe tends to become oval a little bit. Now, this is highly, highly exaggerated. It's nowhere near that, the actual ovalization. But it shows basically the type of deformation and the mode of deformation. The stress that comes into, that gets created in the pipe because of this type of action is through thickness bending. It's basically a local bending in the circumferential direction, right? And then over here, it shows that through the thickness, that stress changes from compression on one side to tension on the other side. And this is the wall thickness, right? Okay. Now, on the longitudinal direction over here to the right-hand side, when you have a vehicle crossing the pipeline tends to bend, as you can see schematically in this figure. That creates a global bending moment. This mode of deformation, this is called global bending. There is also a local bending, which is similar to what we have on the left-hand side. It's in the longitudinal direction instead of circumferential. And that local creates a through thickness bending, much like what you can see here, but in the longitudinal direction. So the CEPA surface loading calculator calculates all those stresses and then adds them together to calculate the total stress. Then the total stress is compared against whatever allowable limits you have for your pipe. So the common models, the commonly used models that are used for surface loading is a model that's known, an older model, that's known as the Battelle model. Technical Toolboxes has two modules. It's the wheel load analysis and the track load analysis, right? These are based on the Battelle model. The CEPA model, which is the new model in Technical Toolboxes, is basically the same as Battelle model. It's just upgraded. So it's an upgrade of the Battelle model. The Battelle model uses Spangler-Iowa equation. So does CEPA. But CEPA is more flexible and I should say more accurate than the Battelle model for a couple of reasons. It's more flexible because there are more configurations that you can analyze on the CEPA calculator. For example, if you have a vehicle that crosses the pipeline at an angle, 45 degree or 20 degree or whatever, you can use the CEPA calculator for that. Whereas in the Battelle model, you can't change the angle. It's always 90 degree or close to normal angle. Another thing with Canadian Energy is that it accounts for the longitudinal stress. If I go back to the slide, previous slide, this type of stress in the CEPA model is calculated automatically. Whereas if you want to use the Battelle model, you have to estimate that manually using, there are different theories that you can use. And then you need to add that to your total stresses yourself. It's not in the tool. There is also API 1102. API 1102 model is a model that is based on a recommended practice. API 1102 is a published report, a recommended practice by API. And it handles surface loading analysis for highway and train, okay? So if you have a highway that crosses your pipeline or a train track that crosses the pipeline, you can use API 1102. And there are two additional modules in Technical Toolboxes that uses this API 1102 model. API 1102 basically is a model that is half numerical, half empirical. What they did, I think it was developed in 80s and maybe early 90s in Cornell University. They performed finite element analyses, and then they verified the results of their analysis with some field tests, right? So that's how the model is developed. It's completely different than the Battelle model and the Canadian energy, the CEPA model, in terms of the equations that are used in the model. It's completely different. Now, which one is a better model to use, CEPA versus API 1102? Both exist in Technical Toolboxes, right? So Technical Toolboxes has both of them. But the decision on which one you should use depends on the situation. API 1102 was originally developed for a bored pipe. So if you have a pipe that is installed using jack and bore or HDD and things like that, API 02 is probably a better model. If you have a trench installed pipe, CEPA is probably better. It also depends on the configuration. For example, API 1102 has some limitations. The pipe has to be perpendicular or almost perpendicular to the road or to the train, whereas in the CEPA, you don't have that restriction. On the other hand, API 1102 is for highway and highway vehicles or train. If you have other type of vehicles like construction equipment or agricultural vehicles, then CEPA is probably more better. Sorry, let me put my phone on silence. All right, thank you. Sorry for that. And then, regardless of which model you use, you got to be aware of the restrictions. And there are a couple of courses that we offer. If you're interested, you can register. You can find them on the website. So the parameters that are influential when you're ready to perform a surface loading analysis, some of the influential and important parameters include pipe internal stress, which I talked about it, so let's pass that. Differential temperature, I talked about it. Other sources. Sometimes you might have other sources for the stress, such as ground settlement, residual stresses from construction, etc. If you have this type of stresses, then you have to, the analysis becomes a bit more complex, and you got to use a different tool. For example, you can still use CEPA and then calculate, for example, ground settlement stresses and add them to the CEPA stresses manually, just in an Excel spreadsheet or like a sheet of paper. So that's possible. Another option, if you have this additional sources for stress, is finite element analysis. But either way, if you have that, your crossing will require a dedicated analysis. Other parameters is the cover depth. Cover depth is perhaps the single most important parameter that affects the stresses in a buried pipe when it's crossed by a vehicle. The cover depth should be known. When you're doing surface loading analysis, there are some input parameters that you almost have to know them. Cover depth is one of them, right? If we don't know the cover depth, there is no way to make a conservative assumption about it. And the same with pipe diameter and wall thickness. Now, the wall thickness, there is a way, if we don't know the wall thickness, there is a way we can make a guess. We can look at the API 5L and just pick the smallest wall thickness. Usually that's conservative. But with the pipe diameter and with the cover depth, we almost always need to know them. So those are important parameters. Now, when the higher the cover depth, the lower the pressure on the pipe from surface loading. That's usually, I mean, that's intuitive. We know that intuitively, that if you have more cover depth, it tends to protect the pipeline against surface loading. But one thing to keep in mind is as you increase the cover depth, the overburden pressure on the pipeline also increases. The pressure from the backfill, soil backfill, right? So, you know, there's a trade-off between the backfill and also the stress from surface loading when it gets to cover depth. Of course, the weight of the vehicle is important. This is another important parameter. We need to know the weight of the vehicle and also the footprint of the vehicle, how many wheels or axles and how much load on each axle. And soil characteristic also can become important. There are a couple of characteristics such as the unit weight of the soil and also the modulus of soil reaction that we usually use for surface loading analysis. If you don't have those values, you can guess, I mean, you can always make a conservative assumption about the soil classification and then guess or estimate those parameters based on soil classification. So if you know the soil classification, there are some tables that give you modulus of soil reaction and unit weight and other things that you need to know. If you don't have soil classification, then you can always go with a conservative assumption. But regardless of what method you use, it's always the best to get soil parameters from laboratory testing of soil samples. All right, so we have here, just to show a couple of simple equations. Here I have the prism load logic that is used in the CEPA calculator. Now, that prism load is not the only way that CEPA uses to calculate the overburden pressure, but it's just one of them. So it basically assumes that the overburden pressure on the pipe is H times the unit weight of the soil. And this 144 is just to convert the units from feet to inches, right? So that's one example of the equations. Another equation that's used in the CEPA calculator to calculate the soil pressure from the vehicle is the Boussinesq. That Boussinesq is given vertical on the pipe is here the Boussinesq equation is provided for a single point load is 3 times the point load divided by in the denominator pi is just the pi number, h is the cover depth, and over here r is the lateral offset between the point load and the pipe. Now, the good thing with using the Boussinesq equation is that the Boussinesq equation can be integrated numerically. And I don't want to go into details, but the point is when you use the Boussinesq equation, no matter what type of footprint you have, you can always model it. So if your footprint is a wheel, you can model it as a single point load or a number of point loads, you know, 6 point loads, like for a vehicle with 6 wheels. If you have a track vehicle bulldozer, you can always divide the contact area into a grid and then assign a point load at the center of each grid point, right? So it's always possible to convert any type of contact pressure into a set of point loads on the ground surface. That's called a load matrix or a load grid. And that's what the CEPA calculator uses in the analysis. There is also an impact factor. Impact factor is because the vehicle in the CEPA calculator, much like all the other methods, much like the Battelle model or API 1102 model, the vehicle is modeled as a static load on the ground surface. In reality, vehicle moves, and because of that movement, it can create vibration and impact. So to compensate for that, an impact factor is introduced into the calculation, and the user can basically assign an impact factor, or it can use the default impact factor. So I talked about the longitudinal stress in the CEPA. I pointed out that in the Battelle model, the longitudinal stress is not calculated automatically. In the CEPA model, the CEPA uses beam on elastic foundation theory to calculate the longitudinal stress from global bending. And this is the equation. Again, I'm not gonna explain how we solve the equation. It's just a numerical integration. But the calculator does this automatically for you, right? So you don't have to deal with any of these calculations. Whereas if you wanted to do it manually, you would have to solve this manually. Right, but again, this equation accounts for this type of global bending of a pipe, and this is called beam on elastic foundation theory. If you're interested to learn more, I have provided a reference here. There is also a local bending, which I talked about in the longitudinal direction. That local bending is calculated from this equation. In this equation, 0.981 is just a constant from elasticity theory, and then under the square root we have 12 times open paren 1 minus nu squared. This nu is the Poisson ratio of the pipe, right? For a steel pipe, that's 0.3, around 0.3. So that's for local stress. And you know, basically it's a quick introduction. I tried not to go into details or deal with the math and things like that. So I think I'm done with my part for today. And again, thanks for your attention.